Okay, this is lesson 1.1, functions. The purpose of this lesson is to demonstrate the difference between a function and a relation. All functions are relations, but not all relations are functions. It's one of those paradoxes. So I'm going to try to differentiate between the two here. The easiest way to describe it is that a function, there's a unique output for every input. That means that every x value will have one unique y value, not multiple. So I'm going to illustrate this through 5 different examples. 1 graphical, 3 numerical, and then 1 by looking at the equation. The first example is graphical. So I'm going to draw quickly a function. I'm going to use a quadratic function here with 5 points. And I'm going to connect them with a smooth curve. And for our non-example, I'm going to use a square root function with 3 points, and then I'm going to reflect it upside down. So we have 2 branches. So it's a square root function and the negative root function, together making a relation. And you can tell the difference between a function and a relation graphically by performing something called the vertical line test. Or the VLT. A function will pass the vertical line test. To pass the vertical line test, you will draw a vertical line across the graph, and if it only touches the graph of the function once, it is indeed a function. However, if you were to draw your line and it were to touch twice, 1, 2, on any vertical line, it will automatically fail the vertical line test, therefore not being a function. Notice this graph does pass the vertical line test at the point 0, 0, but as soon as it fails once at any point on the graph, it is no longer a function and is therefore a relation. And it fits the definition of unique output for each input because, doesn't fit that definition, because if we look here at 1 for x, we would have 2 different outputs, positive 1 and negative 1. Whereas if we look on this graph of our function at 0 for x, we have only 1 unique output, 2. We don't have 2. Algebraically, there's 3 different ways that we can represent our functions and relations. We can represent them by, I'm going to try to keep the graph on there too, by ordered pairs, a table of values, and a mapping diagram. And in all 3 of these representations, you're looking for 2 y values associated with the same x value. And once you have that, you know that it's no longer a function. So I'll show you some examples. First, we'll start with the function. We'll use the actual points on that graph to create our ordered pairs. Ordered pairs is just to create a set and then include all of the points on the graph. And we can use 3 dots to show that there would be more points to the left of the ones we're going to record here in our ordered pair set. We'll start with -4, 2 in brackets to represent that it's a point. And then we'll go with -3, -1, followed by -2, -2, our vertex. And then -1, -1. And finally 0, 2, our last point. And to show that the graph continues, we'll use some more dots there. So there's our set of ordered pairs. And if we look at each x, there is only 1 y value associated with -4. It's 2. With -3, it's -1. -2 is -2. -1 is -1, and 0 is 2. There's no repeated x values producing different y values in that set of ordered pairs. And it might be easier if it's better organized, and the table of values is actually a better organization of your ordered pairs. The table would look like your first x, -4, 2, -3, -1, -2, -2, -1, -1, 0, 2. And you can see there that there's no repeated x values and there's no listing of two different y values for each x value. Therefore, still holding true to the one input, one output. Mapping diagram is kind of a different arrangement again of these same ordered pairs. And I believe it's the easiest to see whether a relation is a function or not a function. So a mapping diagram. We map all of our x values in a circle onto all of our y values in another circle. So our x values are -4, -3, -2, -1, and 0. And our y values are 2, -1, and -2. And notice there's some repeating y values. But what you'll see when we connect our lines here, -4 corresponds to 2. And 0 also corresponds to 2. So two different x values have the same y value, which is okay. What would not be okay when looking at a function is if one x value had two corresponding y values. So you're looking to see if there's only one arrow coming from each x. And if we continue to connect -3 to -1, one arrow, -2 to -2, one arrow, and -1 to -1, one arrow. There's only one arrow coming from each of those x values. Therefore, it holds true, it's still a function. Where we can see repeated x values is when we don't have a function or we just have a relation. The ordered pairs for our non-function, we start, there's nothing more to the left, so I will start at 0, 0. And then we have the point 1, 1, but also -1, or sorry, 1, -1. And 4, 2. And 4, -2. And those keep going. So as you can see here in our ordered pair, 0 has only one output, 0, but 1 has two different outputs, 1 and -1. 4 has two different outputs, 2 and -2. So therefore we don't have a function. And again, we can see it in our table of values. Our x's and our y's, our x's are 0, 1, 1, 4, 4, and we have 0, 1, -1, 2, -2. And what you see in your table is you have repeated 4s and repeated 1s producing two different y values. So we have not a function there. In our mapping diagram, an extra p there. If we map all of our x's, we have three x's, 0, 1, and 4, onto our y's, 0, 1, -1, 2, and -2. 0 has one line just to 0, but 1 goes to both 1 and -1. 4 goes to 2 and -2. Notice we have two lines coming from each of our x's, indicating that we don't have a function. For our equation, you can identify a function if there's the use of function notation and the parent function is indeed a function. So our equation for our first function is quadratic because it follows a parabola and it follows the regular step pattern of over 1, up 1, over 1, up 3, so it's not stretched or compressed. And the vertex is shifted 2 to the left and 2 down. So we would have a quadratic equation that would look like x plus 2 squared minus 2, and it is a function f of x. We could label it as y equals as a relation, because remember, some relations are indeed functions. So this one is more disguised. It's not written in function notation, but it's still a function because the parent function is quadratic. This one's more clear because it's written using function notation. So you have to be careful depending on which version of an equation you're given. You could be explicitly given an equation, or sorry, a function, or you could be given a relation, which is a function when it's one of the parent functions and passes the vertical line test, doesn't have repeated x values. So function notation is a big clue. But it's better to just identify the parent function, and if the parent function is indeed a function, you have a function. It's a lot of the word function. In our non-example, we took the square root equation, y equals the square root of x, and then reflected it. So we actually had the relation y equals plus or minus the square root of x. And what we saw from our graph was that since it didn't pass the vertical line test, and from our numbers that it had repeated x values for different y values, we did not have a function. That's it for part 1 of our video. Please continue in part 2.